Okay, in this video, we're going to talk about type 2 ionic nomenclature. And just to quickly review, when we talk about ionic compounds are always compounds that consist of a metal and a nonmetal. Okay, so the difference between type 1 nomenclature, ionic nomenclature, and type 2 ionic nomenclature. Type 1, we're mostly dealing with elements that are from the alkali metals, elements that are from the alkaline earth metals, and then you got aluminum, gallium, indium. All right, so these are your type 1s, and the reason why we call it type 1 is because these metals only have one oxidation state, or they only have one charge. Okay, now which is going to be different from our type 2s. So our type 2s basically are, in a nutshell, are from your transition blocks. All right, now what makes them kind of a little bit different is that these guys can have multiple oxidation, or they can have multiple charges. So what do I mean by that? Well, let's just look at, for example, let's look at gold. Okay, so gold could either have, in reality, gold could be either silver, sorry. Gold could be either AU plus 1 or AU plus 3, okay? So that's gold. While we have something like copper is typically either Cu plus 1 or Cu plus 2, okay? Iron sometimes are Fe plus 2 or Fe plus 3. All right, manganese could be multiple different types of oxidations. And so here, this is the reason why we call them a type 2, is because these metals could be different oxidations, okay? So how do we determine that? How do we show the difference, okay? So what we do with type 2 nomenclature specifically, all right? So with type 2, we have what we add within the names itself are Roman numerals, okay? So the Roman numerals, okay, basically illustrates the charge or the oxidation of the metal, okay? So for example, if we have, we typically write copper 2 chloride. So copper 2 chloride is just telling us, when we see this Roman numeral here, this Roman numeral tells us that copper in and of itself has a charge of plus 2. And we know that chloride, if we look at the periodic table here, chlorine typically only needs to gain one more to become a noble gas, one more electron to become noble gas, so it will have a -1 charge. All right, and so here what we see is that we have a copper that has a plus 2 charge and a chlorine that's a -1 charge, and that's the way we kind of look at it. So let's just go through a couple examples of writing chemical formulas from the names itself of a type 2 compound. All right, so for example, let's just say we have titanium 3 nitride. Okay, so here's our example. So let's write the chemical formula. So we need to know the charges of each of the ions. So here when we look at titanium, the Roman numeral tells us the charge of titanium. Since this is 3, we say plus 3. All right, now we have nitride. We look at the periodic table, we find nitrogen. Okay, we see that it's so much easier for nitrogen to gain 3 more electrons to be just like neon, to look like neon. All right, and so this will be a -3. All right, so if you notice, this is a 1-to-1 ratio. So when you write the chemical formula for titanium nitride, it's simply TiN. A couple of things I want to note. All right, if you notice, is that the Roman numeral, once again, just talks about the charge, okay? And so oftentimes we find that people want to write, when they're writing the chemical formulas, they write it as Ti in parentheses 3N. See, this right here is completely incorrect, all right? We never, ever put the Roman numerals in the chemical formulas. It's just simply not allowed. So it's not something that we do, okay? All right, so let's look at another example, all right? So let's just say we're writing the chemical formula for manganese 4 oxide, okay? So manganese, as we see here, has a charge of +4. So that's its charge, +4. Oxygen here has a charge. So if you look at oxygen, we could look at the periodic table. You find that it only needs to be 2 more electrons to look like neon, so it will have a -2 charge. Now, what's the chemical formula? So one way I kind of like to look at this, especially when the numbers are a little bit different, I like to figure out what's the least common multiple between these two numbers here. All right, and so between 4 and 2, the least common multiple is 4. Okay, so how many times 4 goes into 4? We said it goes there once, so you have Mn. All right, so that'll be 1. And how many times 2 goes into 4? It goes in twice, so it's O2. So your answer for this problem is simply going to be MnO2, and that's manganese 4 oxide. And just to kind of go through one more example, let's say we have iron 3 sulfide, okay? So we want to write the chemical formula for iron 3 sulfide. So this is our charge. It's a +3. Sulfide, if you look at the periodic table, whoops, I'm trying to erase that. So you look at the periodic table, we have sulfide that's right here. We see that it's only 2 away from argon, so this will have a -2 charge, okay? We know that the least common multiple between 3 and 2 is 6. How many times iron goes into 6? Well, it goes in there twice, so it's Fe2. How many times sulfide goes into 6? It goes in there 3 times, so it's S3. So this is your chemical formula for iron 3 sulfide. So just to emphasize a point very quickly that you see here, that even though you see this is the Roman numeral 3, next to iron doesn't have the Roman numeral 3. Remember, the Roman numeral emphasizes the charge or talks about the charge of the metal, not how many. And again, you should see that here where you have manganese 4, but if you look at the subscript for next to manganese, it's just a 1. All right, so please don't get that confused. Okay, so now let's go backwards. All right, let's start from the chemical formula and write the name. Okay, so like for example, let's say we have this compound here. We have SCCl2. Okay, now the thing about transition metals, as I said, they can have multiple oxidations or multiple charges. So by looking at the periodic table, you cannot easily just figure out what's the charge of the nonmetal. Of the metal itself. So you're going to have to rely on the nonmetal to figure out what's the charge of the metal. Why is that the case? Well, if you notice, all ionic compounds, it has an overall charge of 0. Okay? We know that to be sure, while the metal typically has a positive charge and the nonmetal will have a negative charge, okay? And so these charges will always cancel them out so that the overall compound will be neutral. So if that is the case, then if we know the charge of the nonmetal, then we could figure out the charge of the metal, okay? So for example, we know that chlorine, right, has a charge of -1. Well, how many chlorines do we have? Well, we have 2 of them, so that means this has an overall negative charge of -2, okay? If that is the case, for this to equal 0, the whole compound to equal 0, this one scandium has to have a charge of +2, okay? So when we're writing the name of this compound, we will simply write scandium. The charge of scandium is 2, so Roman numeral 2, chloride. Okay, and that will be the answer for this problem. So to kind of track back a little bit, so once again, we don't know what's the charge of this transition metal, because transition metals, they typically have multiple oxidations, so we just simply don't know. But we have to use the nonmetal to help us figure it out, because we know the charge of the nonmetal. Nonmetals typically only have one oxidation or one charge. So in this case, our chlorine here, we see here has a -1 charge, okay? And simply because there are two of them, oh, that's a bad color. There are two of them, all right? We know that it has an overall negative charge of -2. And if that's the case, then the charge of scandium has to be +2 in order for this to equal 0. And so we know that the charge of scandium is our Roman numeral, okay? And then we just simply write scandium 2 chloride. All right, so let's kind of look at another example. So here's another example. All right, so we have CO3N. CO right here is cobalt. It's a transition metal. So the charge, we don't know. We can't tell just by looking at the periodic table. So we gotta use the nonmetal to figure that out. So what's the charge of the nonmetal? Well, here's our nonmetal. Nonmetal is nitrogen, and we know that it needs 3 electrons to look like a noble gas. So the charge of nitrogen is -3, okay? If so, that's the case, the charge of nitrogen is -3, and if the overall compound has a neutral charge, okay? So that simply means that one nitrogen is -3, and that all the cobalts combined, all 3 of them combined, has to give you a +3 charge, okay? But when we write the Roman numeral, we always write it for each individual element or each individual transition element. So what is the charge of each cobalt? Well, if all 3 cobalts is +3, then each cobalt has to be a +1. This plus is our Roman numeral. So when we write the compound, we'll write cobalt 1 nitride. And that's the name for this chemical formula. So let's try one more example. All right, so we have this chemical formula, Cr2O3, this ionic compound. Cr, if you notice, it's right here. So it's a transition element. We do not know what's the charge. It's a transition, so it could be multiple. All right, so we got to use the nonmetal to help us figure out what's the charge of the metal. So oxygen is here, and we notice that it needs only 2 more in order to become a neutral compound. So when we see that, then we know, okay, well, each oxygen has a -2 charge. Okay, so if that is the case, and there are 3 oxygens, so we have a total of a -6 from the oxygens, from all 3 oxygens, because we know that each oxygen has a -2 oxidation or -2 charge. And so for this compound to be neutral, overall to be neutral, that means both the chromiums together has to have a +6 charge. Okay, and so now we want to know, okay, what's the charge for each chromium, because that's going to be the number that we're going to use for the Roman numeral. If both of them together is a +6, that simply means that each chromium is a +3 charge. Okay, and so when we write this, we'll write chromium 3 oxide. Okay, so just to quickly review, when we're talking about transition metals, all right, typically they have different oxidation states, okay? And so there are some exceptions here and there, but pretty much these guys have different oxidation states. And also we have the heavy metals. These guys typically have multiple oxidation states as well. You have tin, lead, antimony, bismuth, polonium. So oftentimes when you see them written in a chemical formula, we often find Roman numerals as well because they also exist in different oxidations or different charges. All right. And when we are using these metals, we have to use Roman numerals so that we are clear and we could communicate which oxidation are we talking about or we're dealing with when we're coming up with the metals, okay? And when we're writing the name itself from the chemical formula, we have to use, since we don't know what's the charge of the metal just by looking at it, we have to look at the nonmetal, all right? And so by looking at the nonmetal, we know the charge of the nonmetal, and we know that the overall compound has to be overall neutral, all right? And so if that's the case, it's kind of like algebra. You're setting it up to 0. All right, so once we figure out the charge of the nonmetal and the total negative charge of the nonmetal, then we know that the opposite is the total positive charge of the metal, okay? And depending if we have multiples of the metal, like such as 2, then we could just simply divide by the total charge, and which give you the charge of each individual metal atom. All right, and then you just simply write it just like we write type 1. You write the full metal name like you see here, okay? Then you write the nonmetal name with the "ide" as a suffix, and the only new thing here that you find is that we use the Roman numerals, all right, to represent the charge of the metal, okay? Never, ever, it doesn't ever tell you how many of metal ions are in the compound, but what is the charge of the metal.